Okay, welcome back. Part 2 of Chapter 1, and again, this aligns with the Merrill textbook. In the Merrill textbook, they talk about matter, energy, conservation of mass and energy, and then they talk about chemical engineering. And we talked briefly in the last video a little bit about chemical engineering in terms of jobs and things like that. All right, matter and energy. So, chemistry is the study of these transformations in matter and energy. And you're not creating matter or energy. You're not God. You're just taking those things and you're transforming it and from one thing to another. So if you start off with 5 grams of chemical A and 5 grams of chemical B, when you react them, you're going to get 10 grams of product. You haven't done anything other than converted that 10 grams of reactants into 10 grams of new materials. But those transformations are important. Oh, yeah, by the way, we always start with a picture of a teacher. So there you go. Visualize that guy. He looks pretty upbeat. I think he's a college professor, but I'm not sure where I stole the picture from. All right, states of matter. They think that you remember what solids, liquids, and gases are. And you might have been taught that there's a fourth state of matter called plasma. And we're going to get into the particle physics of solids, liquids, and gases later in the course. You should be aware, of course, that they exist and that they represent different forms of matter. But there's actually, I think there might be 8 different forms of matter, and you only need to know 3: solids, liquids, and gases. Plasma, for instance, is when you heat up a gas with so much thermal energy that it knocks the electrons off of the atom. So plasma tends to exist near the surfaces of stars. But there's also things like Bose-Einstein condensate, and that exists when you are at what's called absolute zero temperature or 0 Kelvin. Now, absolute zero temperature, Kelvin scale is measured on how particles move. So at 0 Kelvin, you have no particle motion, and the particles begin to clump together. There's also something called quark-gluon plasma, and that is when the material, remember I said that with plasma, you're going to heat it up above 10,000 degrees Celsius. You're going to knock the electrons off of it. So it's a gas where the electrons have been knocked off the atoms. Well, here we're going to continue to heat it, and now we're going to start to break apart the nucleus. So the quarks and the gluons hold the quarks together, and the quarks are part of what makes up protons and neutrons. So those atomic guts, for lack of a better way of saying it, is starting to come apart, and we're going to study that in chapters 4 and 28 later in the course. And then there's degenerate matter, and this is where you have a gas that is so compressed that it behaves like a solid, and you find this in the core of a star. And then they think there might be an 8th one that they discovered last year, something called quantum energy, what they call topological superconductivity, that they want to use for quantum computers. And very interesting thing if you study it. We're talking about computers that are literally millions of times more powerful than the computers that we use right now as a result of harvesting and using this form of matter. So anyway, so what do you need to know? You need to know that matter exists, and that what all matter has in common is we're talking about relationships among particles. A particle in a liquid behaves differently than a particle in a solid. With a liquid, we can create flow. We could take a liquid and the particles slide over top of each other and pour, and that doesn't happen in a solid. So again, we're talking about interactions among particles. Now, what does your book say? Because your book gives you a very basic definition for you to mesmerize for the test. And here we go. Matter, anything that has inertia, one of Newton's 3 laws. All right, so we're looking at Newtonian physics here. So it resists changes in motion. In order to do that, you have to have stuff. So solid, liquid, gas, you have to have stuff in order to be able to resist that motion. I always like to remind students that this is really what we should think about. Anything that has mass and takes up space. So we can measure the amount of that material, that stuff, and we can measure how much space it takes up, and that term for taking up space is called the volume of the object. Now the second transformation involves energy, and again, here's the definition. I know it's definition. I know it's not mesmerize, it's memorize. But anyway, definitions, mesmerizing definitions is the lowest form of intelligence. I mean, it's not hard to memorize a definition. And so it's not higher level thinking, like taking this information and applying it to make something new would be the highest level thinking. So just by way of saying it, because yes, you should know the definitions. It helps you to understand the material. But again, it is just a definition. So I love this definition: property that is possessed by matter, allowing it to do work. All right, so it's not really a thing in the way that we think of a thing. It's more of an abstract concept, but yet we know energy when we see it, right? Heat, light, sound, electrical, chemical, nuclear, solar. We know it. So what do they mean by allowing it to do work? Okay. In order to allow things to do work, remember from middle school physics, work is equal to force times distance. In other words, we're doing two things here. We're causing motion and we're overcoming forces. That's what we mean by it has the ability to do work. So without energy, we can't overcome forces. Everything would clump together. Without energy, we can't change or create motion. So, and again, the important concept here is that it's very difficult to separate conceptually matter from energy. I mean, energy is possessed by matter. And so, therefore, there's a very intimate relationship between the two. Okay. So, what is that relationship? Because this is a very short video. The relationship, we'll come back to this in a second, it's called the law of conservation of mass and energy. Again, that understanding that when we do chemistry, we are just translating these things. If something has 100 joules of potential energy, we can convert that to 100 joules of kinetic energy. But we're not going to be able to take 100 joules of potential energy and convert it into 1,000 joules of kinetic energy. It doesn't work that way. There is this conservation effect. Again, 5 grams of chemical A plus 5 grams of chemical B gives you 10 grams of product. You start with 10 grams, you end with 10 grams. You start with 100 calories of energy. I changed the unit, I know, from joules to calories. You end with 100 calories of energy. And why is that concept important? Well, it allows us to make predictions about things. And I'm going to say usually, because there are some other things to consider that complicate it. For instance, we have to consider what's going on in the environment around us, because the environment we're going to find is a limiting factor in how we're able to translate these materials from one thing to another. Lastly, they think you know a couple different ways of classifying energy. One is the difference between potential and kinetic. And whenever I ask this, you guys love to use that roller coaster example. Oh, when the roller coaster is at the top of the hill, it has 100% potential energy and no kinetic energy. Well, that's not true. The particles are still in motion. But anyway, let's say that that was true. And then as the roller coaster goes down the hill, that potential energy is converted into kinetic energy. Okay, that's not a bad example of it. And when I do essay questions, I like examples. They help clarify things. But do understand that regardless, that's only one type of potential and kinetic energy, and that's based upon gravity. So that's gravitational potential we're talking about. And you're welcome to use gravitational potential as an example, but there's other types of potential energy. There's kinetic potential. When you have a positive charge separated from a negative charge, we call that voltage. That is the chemical potential, because positives attract negatives. It therefore has the potential to move towards each other. And then we also have chemical kinetic energy, which is the electricity itself, which is measured in amperage. So the movement of that, the kinetic version of chemical energy would be, electrical energy would be amperage. So again, you're welcome to use whatever type of example you want, but do understand two different versions here, how we classify energy, and both of them are very, very important. And again, an intimate relationship between the two. They are married to each other. We always have some potential energy and some kinetic energy. And then the last one is radiant energy, and the reason why this is important is because the phenomena of creating light is created when electrons vibrate. And that's going to allow us to analyze materials. It's going to allow us to take a look at what type of atoms they have, and how many electrons and how they interact with each other. So these electromagnetic waves, these light waves, are very important in terms of analyzing material. Radiant energy, energy transferred by electromagnetic waves. All right, so again, what do we mean by electromagnetic waves? Electromagnetic wave does not need a medium in which to travel through, like a sound wave does. You need a solid, liquid, or gas to transfer sound from one place to another. Light doesn't require a medium. Also, sound waves are what we call longitudinal waves. They're compressed and they stretch, whereas electromagnetic waves look more like that, that sine function from geometry, and you probably learned it like this. Oh, here's how the energy moves. So again, we're going to go over this in chapter 4, and actually we're going to extend that to chapter 6, all the way through chapter 6, because this is an important concept. But for now, you just have to know, again, the definitions and maybe some examples to go with it. And that's really it for chapter 1. Like I said, easy stuff when I put it on that study guide. Very easy. All right. Thank you very much. Catch you on the next video.